So what we are going to do now is simply to set up the equations which lead from this expression for the second order contribution to the energy. And as I said, if we look at the expression here, we have actually seen something similar before. What we have to be a little bit careful with now is the way we also define the Hamiltonian here, because we have redefined the Hamiltonian for a so-called new vacuum state. So let's take a closer look at the way we did the calculations for the FCI case. So what we want to calculate now are these specific contributions, which are given by phi 0, and then h of I, and phi of m here. Now, in FCI calculations and in the other machinery which we developed for Hartree-Fock theory, as well as density functional theory, what we had is that the Hamiltonian was something which we rewrote as E0 reference, plus this term f of n, plus this term v of n. And this is the way we actually rewrote the Hamiltonian for the new vacuum state. And when we now look at the reference energy, this is just a constant. And since we are calculating expectation values between the ground state and states which are not the ground state, that means that an eventual term like this ERF disappears. Now we have to be a little bit careful with the f of n term. So the f of n term is a term which contains also the unperturbed part. So in our case, what we have, when we write out the operator, just let me quickly remind you of that. So there is no problem with a two-body operator, but this one-body operator is modified with a contribution from the two-body operator, as we discussed in the very beginning of the semester. So this Fn or V of n, they are operators which are normalized to the new vacuum. And that's why we get this reference energy contribution. So we don't need to think of that one. So let's be a little bit careful now when we look at these contributions. So P of V of Q, and the way we are setting it, that one up, is that this is an expectation value of this quantity here. And we have a sum over J, and then we have an P of J. These are states below the Fermi level. And then I have my V, and then I have my R, Q of J. And this is an anti-symmetrized matrix element. Now, in our case here, and this is the standard approach in many-body perturbation theory. Here, what we have is that a term like the first one, which is present here, so P of H0 of Q is actually equal to an epsilon P of delta PQ. If this is a Hartree-Fock basis, that is not necessarily the case. So by construction now, it means that many of the contributions which we are going to look at, they will give a vanishing contribution to that because they will involve particle-hole excitations. But in principle, our Hamiltonian should not include this term H0, but it would include the second term. So that means that we are going to have a modified one-body operator. So just keep that in mind, because we have included this piece with H0 in the unperturbed basis. And when we now are looking at the perturbation, we're actually looking at the two-body interaction only. So that means that the term which we should retain should be this term plus the two-body interaction. So we have an additional term, which is V of n, which is 1 divided by 4. And then we have the sum of PQRS. And then we have an P of Q of V of RS, anti-symmetrized. And then we have the operators. We won't make an error if we include the full F, because that operator there contains this piece, and essentially all contractions which we will look at, they will lead to this being 0, because we have by construction made this assumption. So we have a unperturbed basis, which is this basis here. And that's the one which we use as a computational basis. So when we are running a Hartree-Fock calculation, we have to be a little bit careful with how we redefine things. But let's now look at these expectation values. So if I now take this specific matrix element, which we have here, this one. So you see that this is just a squared matrix elements. We have assumed that everything is Hermitian. So that means that we could actually write this one out as a squared matrix element. But let's now look at the calculation of this specific quantity here. So we have a phi 0 of h of I of phi of n. So this is going to be given by this phi 0. And then I'm going to just write this in terms of fn, but it's a modified one. It doesn't include the h0 term. And then a v of n here. So if I look at the first term, I'm going to have something which now is given by phi, and then I'm having a p of q. I have a matrix element, p of f of q, it's an f prime, and then I have my AP dagger, AQ of phi of n here. So the only possibility we can have, which gives something which is non-zero, is if this guy here is given by a one particle, one whole state. If I have a two particle, two whole state, I will have two operators which will not be contracted. So the only possibility here is that I'm looking at a specific contraction of the type AP, AQ of A of AI. And this is the only contraction which is possible. So this is an explicit one particle, one whole state contribution to that sum which we have here. So this is a sum of an infinity of states. And the next term which contributes, so when I look at the next one of phi of v of n, so what we're going to have then is something which is proportional with, so this is the two-body interaction piece. I'm not writing out all the terms there. I'm not putting up the sums and all these integrals. And then I'm having this guy here. And the only way I can now construct something which is different from zero is if this is a two-particle, two-whole state. Because then I can contract with the new reference vacuum. Then I can contract something like this, which gives a non-zero contribution. So this would be a J and an I here. So this is going to give me 4 different contributions. And when I set everything up, you remember now that this gives us a matrix element of the type IJ of V of AB. That's the expression which I'm going to get here. Now, since I'm calculating this term here, I also have to keep in mind that this matrix element is being squared, but I have 2 interaction terms because I have an interaction term which comes from this one as well. And that means that I'm going to get a factor 1/4 here, because this comes with 1/4, 1/4, so I have 1/16, but then I have only 4 contributions which are leading to this calculation to the final result. So this is going to give me, when I collect these different terms, I am going to get the following contributions. So delta E to second order is going to be given. So my sum M in the first term, which I have here, this becomes, so the first term is a one particle, one whole term. So M is just now the collection of one particle, one whole contributions. So I'm summing over all the I's and A's. And then I'm going to have a matrix element. I'm just going to write this in a more compact way of A. So this is this A prime squared. And then there is an energy denominator here, which becomes equal to epsilon I minus epsilon A. So how does that come through? So we have W0 minus Wm. So Wm in this specific case, so Wm is actually given by epsilon A minus epsilon I, as we calculated yesterday, plus W0. So when I subtract that one, when I subtract W0 from here, this one, that disappears, and then I'm left with epsilon I minus epsilon A. So this specific matrix element, which I'm having here, is just this sum over J, and then I have my Ij, V, Aj, anti-symmetrized. And this matrix element is squared. Actually, it's the emission conjugate times the matrix element itself. So that's the first term. And then I have an additional term, which now runs like a sum over AB. That's going to be a factor of 1 over 4. And we are going to calculate this in more detail next week as well. And then I'm going to get a matrix element, which runs like this, VJAB, anti-symmetrized. But now the intermediate state, if we look at this one, so this omega m, this is now given by H0 acting on a two-particle, two-hole state. And in that case, what I have is an epsilon A plus an epsilon B. And then I have to remove the energies of the particles I'm removing, plus omega 0, which contains the sum over all the hole states. So when I subtract this one from omega 0, then what I get as a denominator is an epsilon I plus an epsilon J minus epsilon A minus epsilon B. And these are the two only possibilities. So what I did now was to move from the compact notation with a given set of many-body states, and I have broken the many-body states M into one, a one-particle, one-hole contribution, and two, a two-particle, two-hole contribution. So this is something which is now a two-particle, two-hole contribution. So that means my phi of M here, in that second case, is just equal to the set of Slater determinants with two-particle, two-hole excitations. So let's now bring this in comparison with FCI calculations. So let's quickly just remind ourselves of the FCI case. So when we did the FCI calculation, which is something we mentioned in the beginning of the previous lecture, so what we had then is we had defined this E0 ref, which is now the same as the expectation value of phi 0 of H of phi 0, which again is phi 0 of H0 plus phi 0, and which we label as omega 0 in perturbation theory, plus the expectation value of phi with the interaction here. And this is what we label now as a delta E to first order. So this is in the calculation in the FCI calculation, and then we took the we calculated in FCI the difference between the reference energy, and then we found that this is equal to one term which runs over this particle hole diagrams, not a particle hole, one particle, one hole contributions of F of A. And remember again that this IF of A here, since we have used an orthogonal basis, the H0 term is 0. So when I look at this term, I have an I H0A, and that is 0 because we have assumed that the basis is orthogonal. If I have a Hartree-Fock basis, I have to be a little bit more careful, because in a Hartree-Fock basis, this term is exactly equal to 0. Okay? Because then it contains H0 and the effective mean field potential. And then I have plus a sum over AB ij, and then I have the unknown coefficients which I get from diagonalization, and I have my ij, v, ab, and these matrix elements are anti-symmetrized. Now, if you now look at what we have, so let's just mark these things here. So these are the coefficients we get when we diagonalize. So if you can diagonalize, you have the coefficients. If you now look at perturbation theory, and we keep in mind that these coefficients are obviously dimensionless, they're just coefficients. So you see you have dimension energy because the integrals here have dimension energy. If you look at what you have here, you have the integral squared, so energy squared, but divided by energies. So that means you have energy again. So the dimensionality is correct. But if you now look close at what we have, you see that this matrix element is something which we have here. And what we could do now is to define a new quantity which comes from perturbation theory at a given order. So what I'm going to do now is just to define a quantity which I call TIA, which is going to be given by A of this quantity F of I divided by epsilon I minus epsilon A. And then I'm going to define a new quantity, and I'm going to put in here a term 1, because this has the interaction to first order. And that defines actually something which is proportional to the wave operator to first order. So I'm going to put a 1 here, just to indicate that what we have here is something which is given to the first order in the interaction. This is an anti-symmetrized matrix element. And then we have an epsilon I plus an epsilon j minus epsilon A minus epsilon B. So I can rewrite my second order perturbation theory energy as a sum over AI, and then I have this TIA to first order multiplied with the matrix element F of A plus, and now I have this term 1 over 4, and then I have ABIJ, and I have my TIJ AB to second order, and multiplied with IJ VAB anti-symmetrized. If I then bring back, because now it's useful to look at this in the FCI case, this is given by AI, and then I have my CIA from diagonalization of I of F of A plus CIJ AB, and then I have IJ of V of AB anti-symmetrized. So what's the usefulness here? We see now that perturbation theory brings in, at every order in perturbation theory, information about the coefficients which we had in full FCI calculations. So if we can diagonalize, obviously, we have these terms. But in perturbation theory, what happens now is that the terms we are looking at, these are the approximations to the corresponding terms in many-body perturbation theory. So that means that this one is now an approximation to this, and this one is an approximation to that. When I go to third order, I will get more such terms. So order by order now, I have a way to construct what full FCI gives me. So what's the benefit here? So suppose now that we have a set of states, single particle states. Suppose that you have n equal 100 single particle states, and you have 10 particles. So we are going to distribute 10 particles in 100 single particle states. That means that the total number of Slater determinants, which you have, in this case, without thinking of symmetries, you can always break it down in specific symmetries and block diagonalize your Hamiltonian matrix. This is given by the binomial factor of little n and uppercase n. So this is given by n minus n factorial times n. So the dimensionality here is way beyond what is typical size for an FCI calculation. So this is roughly the limit nowadays, limit or the computational limit. Limit for FCI calculations. If you now look at the many-body perturbation theory result, on the other hand, if you take a look at the sums which we have, so if we go back to MBPT, what we have now is a sum over 10 single particle states. So we have a sum over AI, and then we have this coefficient TIA, which we can calculate. And then we have these matrix elements, which we can also calculate, like this. So n equal 10 means that we would have 10 whole states. So this means that this sum is 10, and this runs from 11 to 100. So I have 90 contributions here. So if you're thinking of the way we are setting up the Fermi level, so we have 10 states here up to the Fermi level. These are the number of particles we are setting up, and they fill the 10 lowest lying states and then define the ground state for the system. And then we would have up to here, we have put a truncation where we put 100 here. So we have 90 particle states and 10 whole states. So when I'm making this summation now, I'm actually calculating this contribution here by simply setting up a table here with 10 whole states and 90 particle states. So this is not a very big dimensionality. You see that immediately. And my sum here runs from, one of the sums runs from 1 to 10, and the other one from 11 to 100. And these are actually, it's a piece of cake to calculate this. And then if I go to the next term, which is a little bit more complicated and expensive, so this would be 90 to the power of 2. And then ij here, they run from 1 to 10. So that is 10 to the power of 2. So 10 to the power of 2 times roughly 100 to the power of 2. So you have 10,000 times 100. So this is the number of sums you have to evaluate, which is still a piece of cake. So to second order perturbation theory, you see now the benefit, right? I can actually evaluate something. Whereas if I wanted to perform the calculation with FCI, I would be limited by the number of single particle states I could include. So I wanted to bring in these computational aspects because this is extremely useful to think, because else you may ask, why are we talking about many-body perturbation theory? What is the gain? Why do we do it? So the main reason for that is that this is a considerable way of reducing the dimensionality if higher order terms are negligible. So if you have to resum to high order, then you lose the benefit of doing many-body perturbation theory. There is also something else I should say, which comes more into the overarching picture, is that if I am to do second order perturbation theory for the electron gas, this will diverge due to the long range part of the Coulomb interaction. So we can see that. If you're interested, I can show you later. We're not going to have that as an exercise, I'm just mentioning it. But if you're going to use the electron gas and you want to sum over 2 particle, 2 hole, and 1 particle, 1 hole excitations, you will not get a expression for the integrals which will converge. However, you can sum this 1 particle, 1 hole excitations to infinite order, and that will renormalize the long range part of the Coulomb interaction. Actually, this is what we discussed yesterday in terms of this Tam-Dankov approximation. And later we are going to discuss something which is called the random phase approximation. So if I sum this class of diagrams, which means practically to sum 1 particle, 1 hole excitations to infinite order in many-body perturbation theory, then we can renormalize the divergent part of the Coulomb interaction. And then instead of using this interaction which you see here, which will be the bare interaction, we would plug in a V tilde which would be the renormalized Coulomb interaction. But then we should not include one particle, one hole contributions in the summation, because they are already taken into account. So for those of you who have taken quantum field theory, this is probably something which rings a bell, because we would then resum terms, and with these resum terms, they can then be reused as effective terms in the theory. And then we can proceed with the calculation. So in physics, often what we do is we try to find out what can cause problems. And if we can resum some of these contributions to infinite order, then we can renormalize parts of the components of a theory. In this case, we can actually renormalize the Coulomb interaction. So this is a digression which I'm mentioning, because even if the recipe looks simple, there are systems which will give us results which are meaningless at a given order in perturbation theory. So if we now look at, so if we just bring up this one, this is something we can calculate, because this sum here would simply be something which is proportional to 100 squared, and this sum here is 10 squared. So we would have this AB, and then to first order, and then we have IJ, V, AB, anti-symmetrized. Now, the thing is that when we run the calculations, we will not perform a quadruple sum. We will actually rewrite these two calculations here of the amplitudes, as we call them, or the coefficients, as a matrix times another matrix. So we will actually not set this up as a quadruple sum or a double sum here. So let me show you these computational issues before we move on with some more formalities about many-body theory. But I hope you see the link between FCI calculations and many-body perturbation theory. So we have now a recipe where we can, order by order, we can then improve the result here. So this will define what's called the wave operator, the first order, which we will set up a little bit more in detail next week. And this will also include the wave operator, the first order. And if we have a Hartree-Fock calculation, this term is by definition 0. And then we have only this term here. Okay, so let me just say before we conclude something about computational issues. Because when you now are setting up these equations here, it could be tempting just to sum up over all the single particle states. But you can actually set this up in a smarter way. And the way you would set it up is simply to define particle and hole, and particle-particle and particle-hole configurations. So what you would do then is something like this. So we could define, if we now look at the example here, this AB and IJ. So we have this component Tij AB to first order multiplied with the matrix elements V of AB. What I could define now is a quantity I, which indicates the indices I and J. So this refers to possible two-hole configurations. So I could set up all these possibilities in terms of a table. And then I could define a new label, which is now a two-particle configuration. So since I said that we had 90 particle states, and if I don't take any considerations of the symmetries, because typically when you set up these configurations, you would always, since these are fermions, you would always have A less than B when you set them up. And then when you set up the table, so you wouldn't set up a full sum from A to B where you let A and B run over all the numbers. You would actually put some constraint on it. But in principle here, what you have is 90 times 90 possibilities of combining two particles. And for the whole states, you have 10 times 10 possibilities, okay? So what I would define then now is to define an interaction piece, which I'm going to label as a ij, and this is going to be my ij here, and VAB anti-symmetrized. And then I'm going to define a new quantity, which I call for TJI, which is actually the matrix element of this AB, of this operator T, and IJ, which is the same as the matrix AB VIJ divided by epsilon I plus epsilon J minus epsilon B minus epsilon A. And now you see that what I can do is actually rewrite that summation as a matrix multiplication, because I have two matrices. So my object here is something which I would redefine as a matrix, which is this quantity here. And then I have the object here, which is now given by this V matrix. So I can actually rewrite everything which I have here in terms of a sum over I and J. And then I have my TJI multiplied with VIJ. And this is something I can rewrite in a more compact way, like the matrix T times the matrix V. And what you can do then from a computational point of view, you can actually set this up in terms of blocks of matrix elements which are different from zero, because there are specific symmetries. Like if the Hamiltonian does not act on spin, then the total spin of these two guys has to be equal to the total spin of these two guys. And you will never be able to couple. So if the total spin is 1, for this case, you cannot couple these matrix elements with spin equal to 0, because then spin would not be conserved, because there is no spin changing term in the Hamiltonian. If you have rotational invariance, there will be other quantum numbers which are conserved. We have translational invariance that also leads to other quantum numbers which are conserved. And that means that when we set up these matrices, we can set them up in terms of smaller blocks. And that is going to lead to much more efficient matrix calculations. But a matrix calculation is more efficient than actually setting up this quadruple sum. So this is a small computational issue, which is worth thinking on when you're setting up your own code for these things. So you can clearly run over just the single particle degrees of freedom, slavishly, in a slavish manner, or you can rewrite it in terms of efficient matrix multiplication, which can easily be parallelized as well. So these are just computational considerations when your space is becoming large. So the benefit with doing perturbation theory is that, one, everything you see here, order by order, is something we can calculate. We can tabulate the integrals. We know the single particle energies, and this will always be given in terms of integrals and single particle energies. So everything you see here, order by order, can be calculated via tabulated quantities. And the way you would typically run the calculations is efficiently by setting up these matrix multiplications. And then that means that you can actually tackle a very large single particle basis. So I can easily set this up to 1,000 or 2,000 or higher. If I want to do that in many-body, in full configuration interaction theory, I would just be lost here at a dimensionality of something like 40, 60, or even less than that, before I'm actually beyond the computational limit of something like 10 to the 10th Slater determinants. So this is the main benefit. We can actually perform calculations with a huge single particle basis. An FCI calculation can be run. Obviously, we can run it by making this basis smaller. But then, if these states become important, then clearly we cannot perform the FCI calculation. And this becomes a way to circumvent the problem by only focusing on the ground state. What we have done here gives us only the ground state. If I want excited states, then I have to include more states in this operator P. And that is going immediately to give more Slater determinants to deal with, and the problem will grow in dimensionality. But if we are just aiming at the ground state, as we're doing here, then this can actually be done for a very large basis of single particle states. And that is the main benefit of doing these approximative methods. So the way we introduce them is simply because FCI, which would be the ideal, is something which we cannot do by simple reasons, which have to deal with the computational complexity and the explosion of degrees of freedom. Yeah.
Would it be possible to do FCI with like a low truncation and then do another truncation?
Yeah. So what many people would do is actually, yeah, go on. Say it again.
Is that something people do?
Yeah. So you would typically limit the states here and then just push the limit for FCI. And then you could compare that with many-body perturbation theory, what that gives.
Yeah, I meant like if you do the FCI up until like a set inflation point, and then for the remainder of the states
you can do
like to include, you can do a different method.
Yeah.
Because it looks like you use the FCI basis.
Yeah, that is correct. Yeah, that is correct. So you would actually try to evaluate those by approximative methods like many-body perturbation theory. So all the methods beyond FCI, or if you do it stochastically, which means Monte Carlo methods, which we discussed in physics 4411 in the spring, all other methods, they are approximations to the full problem. In a way, everything we do is approximations because we don't know whether the Hamiltonian we are using is the correct one, right? So that's perhaps the biggest problem which we have, is that the Hamiltonian is itself a model.
Is that the standard in the FCI for the first levels?
So you would offer, yeah, that's pretty common actually. But the other approach is that you can define an effective Hilbert space. And then you can use many-body perturbation theory to define effective two-body, one-body, etc. interactions, which you then could use in a smaller space and diagonalize exactly in that space. Then you would have an effective Hamiltonian, which you would have to define by approximative methods. Because in principle, the effective Hamiltonian should be you diagonalizing in the monster space and then projecting down to the small space. But that means you solve the monster problem, right? So the thing is, what I want you to see is actually the bottlenecks of what we can do and how you can circumvent it. But then, since many-body perturbation theory is nothing but a Taylor expansion, that has its pros and cons. The pros are clearly that we can calculate with huge single particle basis states, and order by order, we introduce the same type of correlations which we have in full configuration interaction theory, but we only get them order by order. And then we have to hope that, let's say, 3-particle free hole, 4-particle four hole excitations are irrelevant. If they're not, then we have to label more. If you do nuclear physics, you actually have alpha particle excitations, which are actually types of the 4-particle four hole excitations. And they are fundamental for some excited states in, let's say, carbon-12. There is a resonance, which is called the Hoyle state, which is the reason why we are here. So to describe that one, that's an alpha particle excitation. So when the beryllium fuses with the alpha particles, it can produce carbon-12 in an excited state, which then decays. So 1 out of 10,000 decays goes into natural carbon-12, which we are made up of. So that's an alpha particle excitation. So if I want to describe that with these methods, yeah. So if I want to describe that with these methods, I need 4-particle four hole excitations.
Yeah, in condensed matter, it's enough with 2 variables.
Exactly. So unless you're dealing with strongly interacting fermions, if you're doing that, then you're back into the same problems as before. But it's fun actually, because you're then able to see which parts of the physics is important or not. So it forces you to think as a physicist when you do this kind of, how to say, choices on which kind of methods you want to use. Good question. So I wanted to spend some time on showing the difference, because hopefully that gives a better motivation for why you use these different methods.
You also said that with the perturbation theory, you don't know before you start.
Yeah. Yeah.
Would there be any indications?
So what many people would do then would be to run perturbation theory up to fourth order, and you can sum some contributions to high order if you want to. And then if these are small compared to second order and third order, you could say that hopefully there is a sign that we are safe.
I think it's the same density function.
Yeah.
Because when you, let's say, you try to looking for the converge or the density point,
Yeah.
okay, to interact
Yeah.
the Fourier space, is the same. You can convert the determinate space, but you know if after this figure, so you can say that this space converts, but if after you don't know,
right.
It's possible. Maybe,
exactly. Yeah. So, like in this case, often you do a Hartree-Fock calculation first, because then you would often find many contributions to become smaller. And then you hope that the Hartree-Fock basis is something which gives a better convergence, because there will also be many terms like here, if you have performed the Hartree-Fock calculation, this is automatically 0. And then you have less terms to evaluate. And then you can hope that the convergence is faster. Oh, this is a very good point. Yeah. So if you have problems, there is no way you can hide them away. Unfortunately.
Would be nice.
That would be very nice. Okay, I'm going to stop the recording here.